Alright guys, so this is our third and final video for our Flip the Classroom lesson on polynomial functions of higher degree. And in this lesson we are going to talk about multiplicity of zeros. We're first going to take a look at this through the lens of transformation. So we've got some functions up here, and we're going to evaluate these functions as transformations and then talk about what we can determine about their zeros, right? So first let's take a look at our y equals x plus 2 squared. So this is going to be a horizontal shift of our parabola y equals x squared, and we are going to be shifting our graph to the left 2 units here. And we're going to look like this. Now, if we wanted to evaluate the zeros of this, they would come from the linear factors. So right here we would say that we have y equals x plus 2 times x plus 2, right? And the fundamental theorem of algebra tells us that the number of linear factors corresponds to the number of zeros. And right here what we could say is that we have the zero of x equals negative 2 coming from 2 linear factors, and so we would say that we have that zero of x equals negative 2 with a multiplicity of 2. Now right here, if we're looking at this cubic, x minus 4 cubed, we can say this is going to be a transformation of the graph of the cubic that moves our graph right 4 units. So 1, 2, 3, 4. And if we are taking our zeros from the linear factor x minus 4, we can say we've got the zero of x equals 4. And since it's coming from 3 linear factors, we can say we have that zero with a multiplicity of 3. Next, if we take a look at y equals x plus 3 to the 4th, we can say this is going to be a transformation of the graph of y equals x to the 4th, which looks like a flattened out parabola. Something like that. And basically, the graph of x plus 3 to the 4th is going to be a horizontal translation 3 units to the left. Now right here, when we evaluate the zeros of this guy, what we're going to say is we're going to get the zero of x equals negative 3, and we're going to get that from 4 linear factors, so we would say we have it with a multiplicity of 4. Finally, right here, if we take a look at this linear function, we can say that we've got a y-intercept of negative 1 and a 0 of 1, and right here we can say that this linear function is going to cross like that, and right here we can say that the zero of this function would just be the x value of 1, right? And we would say, we wouldn't really write the multiplicity of 1. In general, if you just have 1, 0, it's understood that the multiplicity is 1, right? But if we were to write it, we could compare what we're seeing between even multiplicities and odd multiplicities. So right here, with our even multiplicities, what we're seeing is the zeros that are those x-intercepts are places where we just come down and touch the x-axis, right? So for even multiplicities, that's looking like we're just going to touch our x-axis. And when we see the odd multiplicities, we're basically crossing the x-axis, right? So in general, we would say that even multiplicities means we're just going to touch, and odd multiplicities means we're going to cross. The other thing that we can say is that when we are hitting the x-axis, we look like our multiplicity. So right here, with a multiplicity of 2, I'm coming down and hitting the x-axis like a parabola, right? With a multiplicity of 3, I'm crossing the x-axis like a cubic, right? With a multiplicity of 4, I'm touching the x-axis like a quartic. And with a multiplicity of 1, I'm crossing the x-axis like a straight line, right? Now, both of these things are traits that we're going to say transfer to polynomials where we have linear factors repeated, right? So if we're looking at f of x equals x minus 2 cubed times x plus 1 squared, then basically right here we can say that we are going to have the zeros of x equals 2 with a multiplicity of 3, and x equals -1 with a multiplicity of 2. Now right here, my 0 of 2 has a multiplicity of 3. That means two things. That means that, first off, I'm going to be crossing the x-axis with this 0, not just touching. And secondly, I can say that I'm going to be crossing the x-axis like a cubic. With my 0 of -1, I can say that I'm going to be just touching the x-axis, right? Not going across it, but just coming down and touching it. And I can also say that I'm going to be hitting the x-axis like a parabola, right? So I'm going to be basically touching like a parabola and then going back from the x-axis instead of crossing. Now right here we can say that the degree, of this polynomial would be 5, since we're multiplying 5 linear factors, 3 here and 2 here. And right here, if we think about what we would get for a lead coefficient by multiplying all those x's, we can say the lead coefficient would be a positive 1, but more importantly, we can identify that the lead coefficient would be positive. Now this tells us about our end behavior, right? We've got a polynomial of odd degree with a positive lead coefficient, and that means that we're going to be coming from -infinity and going to positive. We also know where we're going to be hitting the x-axis at -1 and at 2. And we know how we're going to be hitting the x-axis with those x-intercepts. Right here I know that I'm going to be coming from -infinity, and I know that I'm just going to touch the x-axis at -1, like a parabola. And then I'm going to come back, and I'm going to cross the x-axis with my 0 of 2, like a cubic. And this would be a rough graph of this function. Now, what we want to point out here is that we don't know where this min is, right? It's going to happen somewhere in the on the negative y-axis, but we don't know how far down we are. Really what we can say is that we've got a rough graph of our polynomial right here that does not take into account scale, right? So this doesn't take into account scale specifically for the y-axis. So right here, this could be way down at 100, or it could be, up at 2. We really don't know. But in general, we've got a rough graph of the function in terms of just its shape, from the end behavior and from the zeros with their multiplicity. So what I want you guys to do is try this on your own. We're going to identify the degree, the zeros and their multiplicity, and then the end behavior. And then what I want you guys to do is to bring all those things together with the graph, right? So right here, we're going to be able to attack A, just like we looked at the last one. But with B, what we're going to have to do is factor this guy out first. Now, we're going to be able to identify the degree and the lead coefficient easier, right, to give us the end behavior. But we're going to have to do a little bit of work to find the zeros and their multiplicity. So right here, what I want you guys to do is to pause the video here and give this one a shot, and we will come back and look at this in a second. All right, guys, so looking at our first one, we can say that we have a degree of 4 since we're multiplying 4 linear factors. And if we think about what we would get for a lead coefficient, if we multiply only positive x's, we can say we would have a lead coefficient of +1. So immediately we know what our end behavior is going to be, right? With a even degree and a positive lead coefficient, we can say we're going up to positive infinity on both sides, right? Now basically what we can think is, if we're going from left to right, that kind of means that we're going to be coming from positive infinity and going to positive infinity with our end behavior. Right here, we can look at the zeros. We're saying we have a 0 of 2 with a multiplicity of 3, right? And a 0 of -3 with a multiplicity of 1. So that basically means that we're going to cross the x-axis with both of these zeros. At -3, we're going to cross like a linear function, since we've got a multiplicity of 1. And at 2, we're going to cross like a cubic, since we've got a multiplicity of 3. So drawing this graph out, we're coming from positive infinity. First, we're crossing at -3 like a straight line. And then we're going to come back up to the 0 of 2 and cross at 2 like a cubic. Looking something like that. Okay, so our next function, we can first determine the degree and the lead coefficient pretty easily because it's in standard form. So looking at this guy, we can say that we have a degree of 3 and a lead coefficient of -2, right? And basically what this is going to tell us is we see that end behavior coming from negative infinity and going to positive infinity flip. So we can say that we're going to be coming from positive infinity and going to negative infinity with our end behavior, right? Now we have 3 zeros, all with a multiplicity of 1. We've got the 0 of 0, negative 3, and positive 3, so we can sort of mark those off. Sort of say there's negative 3, there's positive 3, and here's 0. And since we've got a multiplicity of 1, we know that we're going to be crossing at each of those zeros, and we're going to be crossing with a straight line. So basically, our cubic is going to look something like this. Coming from positive infinity, crossing at negative 3, coming back up, crossing at 0, and going back down and crossing at negative 3 again, and then going back down to negative infinity. Now again, these are the rough shapes of these functions, and we don't know, what the mins or the maxes are in terms of how far up or down we're going on the y-axis. But we can sort of get a general idea about these shapes by just looking at the zeros and their degrees and the end behavior. So end of the last video here, guys, and I will see you guys in class on Thursday.